Voice Recognition App. In this section, we will learn how to create a model capable of recognizing basic voice commands. In this video, we will see two approaches to perform voice recognition, our approach, then we will explain the problems that we may encounter, and we will describe the model and the dataset used. Normally, when we think about analyzing audios, the first thing that comes to our mind is the spectrogram, which represents the frequency of the sound. One can use the spectrogram in different ways, depending on the application we want to develop. For instance, for speech recognition, recurrent neural networks can take the spectrogram from the voice directly and classify sound into text in real time. On the other hand, when we want to classify a whole audio file, we can just create a fingerprint of that sound and train a model with it. Shazam uses this approach. In case you don't know Shazam, it's an app capable of recognizing a song given a piece of it. So if you're in a bar and you want to know the name of the song it's being played, you can record a few seconds of it and it will tell you which song it's. I don't know how it exactly works, but it's definitely based on classifying different audio fingerprints. And I guess for each song, they generate several fingerprints, so regardless of the section being recorded, it can recognize the song. We will do this last approach because we can reuse the models we developed before. If you are interested in recurrent neural networks, Coursera recently released a course called Sequence Models, where you can learn a lot about this type of networks. MFCC, which stands for Male Frequency Cepstral Coefficients, are typically used for extracting a signature from the spectrogram. It's out of the scope of this course to explain MFCCs in detail, but just imagine a function where you give the spectrogram together with other details and you get a fingerprint. With this fingerprint, you would typically train your model. Now, I have good and bad news. The good news is that TensorFlow has two nice functions to extract the spectrogram from the audio and the MFCC from the spectrogram. The bad news is that it's not compatible with TensorFlow Lite. As I've mentioned before, they want to keep TensorFlow Lite simple and light, so it will be up to the developer to implement his own spectrogram and FCC function in Android or iOS. Since implementing MFCC would take much time and it's purely mathematical, I will skip that part and I will simply take the spectrogram as an input. The only procedure between the spectrogram and the model will be a normalization of the spectrogram values. Given the same voice command, spectrogram will be different depending on certain circumstances. For instance, it's not the same saying stop, or tone difference like low and high pitch, the different timbre each person has, the volume and background noise. All of this can be sorted out by having enough data. When applications of this kind are developed, developers gather samples from different people and add artificial background noise and change the volume. I won't do any of those things for this example, since in a controlled environment it will work anyway. What I will do is to shift the signal 100 times, and as a result I will have sometimes unrealistic spectrogram. The goal of this is that regardless of the location of the word in the spectrogram, it will be able to recognize it. By the way, if you're wondering what is that long up-down at the beginning of the spectrogram, it's just noise my microphone does. Data will be also normalized and adjust. Normalization will simply enclose the data in the range between 0 and 1. In addition, since the network input is expected to be like 10,000 values, we have to adjust our spectrogram to fit the network. If our spectrogram is bigger than what we need, we will sample 10,000 values equally spaced. On the other hand, if it's smaller than 10,000, we will just pad both sides with zeros. What we will do with the histogram is something very simple. We will reshape it to be a two-dimensional matrix of size 100 by 100, and we will reuse the same code we wrote in section 3. Although models can be reused for different problems, that doesn't mean those models are optimal. A good model is a model capable of minimizing properly its cost function, and this depends also on the training data. This is the same model used in section 3 for handwriting recognition. The only difference is the shape of the filters and tensors, and the last layer will be removed to make it simpler. Since we will have 5 different classes, the output shape will be 5. The dataset will consist of 5 recordings of each class: OK, high, go, left, and right. So we will have a total of 25 samples. In the next video, we will start writing the model.